Blockstore, secure, public-private storage protocol. In the previous overview on directory copy, I didn't go into any detail about what it meant to encode a block. That video was already too long. I'll cover that in this video. It is very important how we encode blocks. The method we use to encode the blocks will allow us to implement features in the store itself. First of all, in this store, our primary objective is to never do anything twice. That includes encoding blocks. So the first step is to identify what block we're dealing with. Take our data domain and our block of data, and then perform a cryptographic hash. If the block doesn't already exist in the store, we then compress it. We also want this to be a secure store, meaning we should encode the block on the client side, transport it to the server, but the server should have no mechanism of decrypting it. But wait, we're making a public block store that also has encrypted secure blocks? We do this by dividing the hash of the block into two parts, a key and an ID. The key is the hash, and the ID is a hash of the hash. Our final step in encoding this block is to place the ID after the encrypted blob, and also append a hash of the encrypted blob after that. All these parts together make up our encoded block. Let's recap what this lets us do. We can transport a block to a storage server, and without knowing the contents of that block, that storage server can validate that the block is still valid. Also, without knowing the contents of that block, that storage server can advertise if it has the block contained inside of the encrypted blob. Only the client, which knows the data domain and the original key which it didn't transport to the server, can request and decode the block. There are numerous benefits to this design. One, for example, the data doesn't constantly need to be encrypted and decrypted as it's transported, say from the transport layer to the storage layer. There aren't vectors of attack in between these transformations. The block remains encrypted and secured. The performance profile of our storage servers is dramatically reduced. Synchronizing and managing data on those storage servers is dramatically simplified. Synchronizing data across different storage clusters is also dramatically simplified. Since each encoded block is a black box, security policies are irrelevant. With all these properties in place, we can easily construct a storage cluster. Using the images from our directory copy video, a store would be a network interface that encapsulates an image. Each of these stores providing a query and a store interface. Synchronizing data across multiple stores is an easy matter. Pushing data to these stores is equally as convenient. Here's some things to look for as I demo this project. This is a modern C++, test-driven development, open source project. You can access the code on GitHub. Encoding happens once on the client side, and all storage servers are blind. The block is a black box. There isn't a constant chain of encoding and re-encoding occurring every time the abstraction layer changes from transport to storage. Blocks are never re-encoded. The channel doesn't need compression, encryption, or validation. There is no CPU load on the server. Data domains, or SALT for our block hashes, partition data when desired. Although a default data domain would be optimal, especially in situations where data security is not the primary concern. Common data. Metadata about files, directories, or storage volumes is packed into blocks as well, so that any object can be accessed from one key. The synchronization between block stores is optimal. The demo is sped up about 8 times. In this demo, we're backing up 10,000 files, or about 10 gigabytes. We'll first back this up to an image, and then we'll sync it to a store. Some things to keep in mind: since we only encode a block once ever, we want to make sure we get the most out of that. Therefore, we use very aggressive compression. Also, the laptop I'm running the demo on throttles at 15 watts, and when I'm recording and running a full CPU demo like this, it actually ends up taking about twice as long as it normally would. The silver lining in this situation is that processor power is being distributed across all storage clients. While this initial encoding is CPU bound, if we were to run the same encoding again, it would finish I/O bound much faster. Because during the second pass, none of the blocks would be encoded again. They would only be identified. Here's the exciting part. After the blocks are encoded, they can be transported and transmitted extremely efficiently. To sync that same 10 gigabytes took, 16 seconds? And there's good news with the aggressive compression. There are still optimizations to be made.